Thank you for being here. My name is Manuel Ramirez, and today I'm going to be taking you on a tour of the universe by basically telling you how the largest structures of the universe can affect the smallest galaxies. My mentor was Dr. Charlotte Welker, and I am part of the Gotham Web Research Lab, and I just want to give a special shout out to them because this is, I think, the only group in the United States that does work into filaments. So that's just an interesting fact. So I'm going to break this up into 5 different sections. 1, the goal of the study. 2, introduction to cosmic filaments. 3, towards filament classifications. And 4, dwarf galaxies and new horizons. And of course, our future works. So the goal of the study was to determine to investigate the influence of cosmic filaments on hydrodynamic behavior and evolution of dwarf galaxies. At this point, I know that's just word salad, so let me get into explaining any of that. First, let's introduce what are cosmic filaments. Cosmic filaments are the largest structures that we know of so far in the universe. They are made up of gas, galaxies, and a whole lot of dust. And they're all held together gravitationally by dark matter. They branch into nodes where they feed large galaxies like our own galaxy, the Milky Way. And these little lines right here are what we call our filaments, the ones that just cross over. Smaller galaxies typically fall below 10 to the 10 solar masses are the ones that stream along towards the nodes. Basically, in red, you can see a little clump of dwarf galaxies, and in the green over there, you can see the node. And the nodes are essentially just groupings of filaments. So let's find out what a galaxy is. A galaxy is a basic collection of stars, gas, and dust held together by dark matter, and they range on scales from 10 to the 4 to 10 to the 12 solar masses, whereas dwarf galaxies are exactly the same, except they fall below 10 to the 9 solar masses, so they're tiny guys. We use the New Horizons simulation, which is a zoom-in simulation, which is 20 megaparsecs on each side. It has 15 Milky Way-sized galaxies and roughly 5,000 dwarf galaxies. It has a spatial resolution of 34 parsecs and a stellar mass resolution of 1.3 times 10 to the 4 solar masses. And this resolution allows us to capture a multi-phase nature of the intergalactic medium. It allows us to see the big stuff, but also actually see where the small stuff are. So in this image, we can see like the central filaments are the ones that go this way and that way, and you can also see the smaller ones that are also resolved, but we can also see nodes resolving here as well. So how do we find filaments in New Horizons? We use a tool called Disperse, which is a discrete persistent structure extractor. Basically what it does is that it allows us to, it identifies the structures within the skeleton that it creates. It forms a skeleton within New Horizons of the cosmic filaments, and it says, like, it finds features that are distinct and that pop out. Those features being voids, which are underdense regions, there are very few particles, walls, which are sheet-like structures, filaments, which are the elongated structures that we are mostly focusing on, and nodes, these dense regions where filaments intersect. And this, on the right side, you can see the skeleton that is constructed with these specific features. To give a little bit more background on those features, the way that Disperse thinks of these features, it basically says that voids are density minimum in all 3 directions. Walls are minima in 2 directions and maximum in 1. Filaments are maximum in 2 directions and minima in 1, and nodes are just maximum in all 3. So how do we find properties of these filaments using our tool Disperse? We first thing that we did was that we took our our cube, which is the full volume of New Horizons, and we made slices of these cubes, and we said, well, what are our hydrodynamic properties? And these properties, in our case, are density, temperature, and metallicity. And as you can see, these specific properties follow along where the filaments are, and they tend to be higher where the nodes are as well. Now let's try to classify these filaments. So once we zoom in into the entire, instead of looking at the entire volume, let's take a look at smaller regions. We zoomed in on structures, and here you can, here you see density, temperature, and metallicity as before. But once we zoom in on these structures, we see that different kinds of filaments arise. Our hot filaments are the ones that are hotter in temperature and are found in denser areas. The cool core filaments they effectively radiate at the spine and form cool, pristine gas. And pristine filaments are the ones that are less dense, less collapsed, and are metal poor, which is why they specifically, well, you don't see it over here, but you do see it everywhere else. So instead of looking at instead of looking at filaments, let's take a look at the galaxies. The galaxies in New Horizons have a lot of different properties. When we take a look at mass versus angular momentum, we notice that the angular momentum, the smaller galaxies have less angular momentum, whereas the larger galaxies have more angular momentum, which is a linear relationship, and that is to be expected. And once we also take a look at mass versus a half mass radius, we also see this relationship, but there are 2 groups that form, the one over here and the one above. And this is, we also see this down here, but this is just an artifact of the simulation. And they follow a sublinear scaling relationship. Now, when we take a look at distance versus median mass, we notice that our larger galaxies are closer to the filament, which is to be expected. And our future works from this study is that we want to determine how properties vary, how galaxies vary around different types of filaments, and we'd like to extend this analysis to the star formation history and eventually the star formation rate of these galaxies around filaments based on their properties. Thank you. Does anyone have any questions? Yes.
The mass versus radius plot had the main blob and then the little above blob. And so,
This one.
yeah. So the above one means at a certain mass, most of them are kind of small, but some of them are a little bigger, I guess. Would that maybe have anything to do with how far they are from the filaments? Or is that a thing you can look for?
That is something that we can look for, but it doesn't have to do with their distance to filament. Rather, it just has to do with, I just believe, the nature of the simulation that we used. Because underneath, you can also see that there's an artifact, but that's just something that the simulation has. Yeah. Great question. Yes?
Say a little more about the simulation, which which code was used, which subgrid model for the star formation, and so forth?
That's a great question. That is something that well, I'd have to look at the paper in order to give you a precise answer.
Okay.
Yes.
So what kind of observations could we use to like do this? Like, the mass resolution is exquisite, but I'm curious about that. Yeah.
So the thing about filaments is that we currently can't observe them because they're just so big. But the mass resolution allows us to observe the structures that are, I guess, within them, such as the galaxies, the larger galaxies, and the smaller ones like dwarfs, and big stars that are within these filaments. Yeah?
Here, I think it was your plots of the filaments. If you could go back to it, I think it was in. It looked like it was in 3D.
Which one? This?
Yeah, yeah. So I'm curious. I might have missed it, but how do you have that data in 3D in the first place?
Oh, it's a good question. So disperse takes an input of, we give it basically, we want gas of this temperature, we want this many metals, etc. And it takes those features, and well, the full simulation is of 20 megaparsecs, and it's a zoom-in region of a larger simulation, Horizon AGN, and it takes our inputs, and this is already mapped out within Horizon AGN. It's just what this simulation would look like. These filaments would look like under those particular conditions.
New Horizon is 3D, correct?
Correct.
There. So.
It's a volume. No? All right. Thank you.